Hello, welcome to my talk all about fluids. This talk is on an interesting topic of whether a viscous fluid could form a potential flow. This is the first part of the talk, with a focus on the theoretical aspects relevant to the topic. As you all know it very well, for a potential flow, the fluid is required to be irrotational and inviscid. And in many cases, the flow is also assumed to be incompressible. The question is, do we need all these assumptions for an irrotational flow? I will answer the question in the talk. Let's start from the 4 Navier-Stokes equation. We can see in the 4 Navier-Stokes equation, in the left-hand side, the substantial derivative is used for calculating the fluid acceleration, which consists of 2 parts, the local acceleration and the convective acceleration. In the right-hand side, the force due to the fluid pressure, the body force acting on the fluid, the dissipation term due to the fluid viscosity, and the fluid compressibility term. The last 2 terms are related to the fluid viscosity. For an inviscid fluid, the fluid viscosity coefficient mu equals to 0. Thus, the Navier-Stokes equation is degenerated to Euler equation. Although Euler equation is not perfect, it is very useful for deriving the Bemoulli's equation, which is actually an integral form of Euler equation under the assumptions of an inviscid and steady flow. This is a conventional assumption for the inviscid flow. In this slide, I would like to clarify the concept of inviscid fluid and inviscid flow. And this clarification of these 2 concepts is very important for irrotational flows. An inviscid fluid is a fluid with 0 viscosity, that is, mu equals to 0. This is an ideal assumption, since all fluids are viscous. However, for many practical applications, this assumption is acceptable because it could simplify the fluid dynamics a great deal, while it still gives very reliable and good approximations to the problem. An inviscid flow is a flow for which the last 2 terms in the 4 Navier-Stokes equation vanish. Obviously, an inviscid fluid will cause an inviscid flow. However, a viscous fluid could also cause an inviscid flow, such as the uniform flows and the incompressible irrotational flows. You will see this clearly later in the talk. Conventionally, there are 2 basic hypotheses for a potential flow, as the following hypotheses 1 and 2. The flow is an irrotational flow. This assumption would lead to a velocity potential function, and under such assumption, the 3 velocity components are no longer independent of each other. the mathematical expression for the rotational flow is the core of the velocity vector is 0, or its circulation of across the curve is 0. The second assumption is the inviscid fluid, mu equals to 0, and the corresponding fluid dynamics equation is Euler equation. However, in many practical problems, the flow is also assumed as incompressible. This assumption could simplify the problem, so for finding the solution easier, this assumption is made for the purpose of simplifying the problem rather than a prerequisite, because we have seen in many cases the compressible flow can be potential flow too. So the question is, for potential flow, do we need all these assumptions? In this slide, I will show you what is the potential flow. In principle, potential flow is an irrotational flow, because this assumption could lead the velocity potential function, and there should be no more assumptions needed for a potential flow. Then what is an irrotational flow? The definition of a potential flow is the circulation of a fluid velocity vector on an arbitrary closed curve is 0. For instance, for the arbitrary closed curve in the fluid C here, its circulation calculated as this. If the circulation is 0, then the fluid is irrotational. Based on the Stokes theorem, we can convert the integral on a closed curve to a surface of the enclosed curve, and from the 0 circulation, we can obtain another definition of an irrotational flow as this: the core of the velocity vector is 0. The physical definition of a irrotational flow is that the fluid elements do not rotate around their own axis while moving around the path lines as this. This is similar to the famous Ferris wheel, on which the capsules are hinged to the large rotating wheel. When the wheel rotates, the capsules keep their upright position all the time, and the passengers in the capsules could not feel any rotation. The velocities of the different positions on the capsule are all same as the velocity at the hinge. For a rotational flow, the fluid elements rotate around their own axis while moving around the path lines as this. In reality, how we can tell which flow is a rotational or irrotational flow? Generally, there are two ways to check whether the flow is irrotational or not. The first one, for checking whether the core of the fluid velocity vector is 0. The second way is to make a closed curve, any closed curve in the fluid if you like, and check whether the circulation is 0. Here, take the co-ed flow as an example. Its velocity distribution is given as this, and the core of the velocity vector given by this is not 0. And if we draw a rectangle in the co-ed flow and check whether its circulation is zero. Obviously, in this co-ed flow, its circulation is not zero. Thus, we can see both methods have shown the co-ed flow is rotational. Now, we may have a question where we can see the rotational and the irrotational flows in practical flows. Here, a uniform flow passes a plate, and it can be seen near the plate surface. There will be a boundary layer where the fluid viscosity increases from zero at the plate surface due to the no slip condition to the same velocity as that of the uniform flow. This layer is called the boundary layer. If we extend the flow to a large range of the flow as this, so we can see in the boundary layer, we draw a rectangle and we can see its circulation is not zero. Thus, the flow within the boundary layer is rotational. And outside the boundary layer, we can see the circulation on a rectangle is zero. Thus, the flow outside the boundary layer is irrotational. Here, we look at the famous example, the flow in a horizontal pipe as this. So when the Reynolds number is small, such as less than 2,300, and the flow in the pipe is nominal, and we can obtain the analytic solution for the fluid velocity distribution as this. This flow is also called Hagen-Poiseuille flow, and it can be seen such a flow is rotational. However, when the fluid Reynolds number is increased, say to 10 million, and the flow in the pipe is fully turbulent, and the fluid velocity profile is something like this. As such, the large portion of the flow is irrotational. Only the region near the pipe wall, here and here, are the viscous boundary layers, and the flow within the boundary layer are rotational. When the Reynolds number becomes very large, and the boundary layer would become thinner. As such, the entire flow may be taken as an irrotational flow for a good approximation. This is a good practice in many practical problems. For a rotational flow, the zero core of the velocity vector would lead a velocity potential function phi, and the fluid velocity vector of three independent components is transformed to a scalar function phi as this. The assumption of a rotational flow could simplify the dynamic problem very much. In a Cartesian coordinate, the three velocity components are calculated from the velocity potential function as this. So, if we obtain the velocity potential function, and then we can calculate the velocity component. Use these three equations. If the flow is incompressible, the corresponding continuity equation could lead Laplace equation for the velocity potential function. We have seen many applications by solving the Laplace equation in the practical problems. This is generally acceptable when the fluid velocity is small, for instance, less than 0.3 Mach number. If the flow is compressible, the continuity equation would lead a partial differential equation for the velocity potential function as this. So we can see this partial differential equation for the velocity potential function is much more complicated than the Laplace equation. And also here we have one more unknown, the fluid density. And we also need to solve the fluid density in the dynamics. Thus, we need one more equation for the problem. For instance, we may use the ideal gas equation. If the compressible flow is steady and the assumptions of an ideal gas and the small disturbance in the fluid field as this, so we can get the partial differential equation for the velocity potential function phi as this. Here m is the Mach number. For more details how we can get this partial differential equation for the velocity potential function can be found in the book Modern Compressible Flow of John D. Anderson. From the four Navier-Stokes equation, we can see to obtain an inviscid flow, the last two terms must vanish. For this purpose, the simple analyses are made for these two terms to make sure these equations are satisfied. The velocity vector gradient tensor or the velocity vector divergence are zero. For instance, a uniform flow can satisfy this. To ensure the term of this and this are both zero, this can be satisfied in incompressible irrotational flow. Since for incompressible irrotational flows, we have this and this. However, for compressible flows, these two terms are not zero. Now we look at the last two terms in the four Navier-Stokes equation for irrotational flows. The last two terms can be written as this, and put this together, we have equations as this. And for the convective acceleration, we can use the vector calculus identity. This consider the flow is irrotational flow, so we can have this. If the fluid gravitational force is the only body force, we can put all this together. We have the equation for the irrotational flows as this. So the integral form for the irrotational flow is given by this. This is the general Bernoulli's equation under the only assumption of a irrotational flow. Here, we don't make the assumptions for inviscid flow or incompressible flow. If the irrotational flow is incompressible, then the term related to the fluid viscosity disappears. So we have the conventional Bernoulli's equation for irrotational flow. This is the same equation as we've seen in many textbooks. However, for deriving this Bernoulli's equation, the assumptions of an inviscid flow is not required, and the Bernoulli's equation is automatically satisfied when the irrotational flow is assumed to be incompressible.